Alright, so what happened here is we have, like we said, law of angular momentum. Your angular momentum equals your moment of inertia times your omega, and where the moment of inertia equals I equals mass for the Earth 2 over 5 times the mass radius squared. Mass of the Earth is, so we have 2 over 5 times the mass of the Earth being 5.98 times 10 to the 24th kilograms times the radius, which is 6.38 times 10 raised to the power of 3 squared, so just make it to the power of 5. This gives you a total moment of inertia of I equals, we got it here, 1.52 times 10 to the 30th. Alright. Now to find the omega, we're going to do omega equals 2 pi frequency, right? And the frequency of the Earth is 1 over 24 hours times 60 minutes times 60 seconds. Makes it 1 over 86,400, I believe is right. Times 2 pi, which brings you to the omega of equals, what is it, 7.27 times 10 to the negative 5th. Okay, now if we plug both these numbers in together, it gives us a total angular momentum of 6.94 times 10 to the 26 kilogram meters a second squared. That's the angular momentum of the Earth. Okay. Now, as we said, the angular momentum in an isolated system such as the Earth will always remain constant. So, if we take these space shuttles, and we're going to say they're very massive space shuttles, a lot of space shuttles that we launched, being a total mass that will be 1 times 10, 1.0 times 10 to the 24th kilograms. That's the mass of the space shuttles we launched. So, that launching that amount of space shuttles reduced the mass of the Earth, which we said was 5.98 times 10 to the 24th, to be 4.98 times 10 to the 24th. Okay. Okay, and as we said before, our omega, that's our angular velocity, before we launched the shuttles was 7.27 times 10 to the negative 5th. Now, this is our overall angular momentum, which will remain constant. So, the only thing we're changing is the mass of the Earth, because we're launching so many shuttles, so much mass of the shuttles that it's taking away from the mass of the Earth. So, as the mass of the Earth changes to be 4.98 times 10 to the 24th, we do times the same thing, times the radius, which is 6.38 times 10 to the 5th. It gives us a moment of inertia of, we need to do 2 bits here. It gives us a total of, where are we at here? 1.27 times 10 to the 30th. Okay, so what we've done here is before, our moment of inertia of the Earth was 1.52 times 10 to the 30th. Our moment of inertia now has been reduced to 1.27 times 10 to the 30th because, once again, the mass of the Earth was reduced. So, our total L, which will remain constant, can be divided then by our moment of inertia to find out the omega. And this, once again, is the angular velocity. This is how much the speed of the Earth will change. It will speed up to compensate for the reduce in I. So before, we were at 7.27 times 10 to the 5th. if we put in these numbers, plug these numbers in, which would be, once again, our 6.94 times 10 to the 26th divided by 1.27 times 10 to the 30th. The answer is omega equals 5.47 times 10 to the -4th. So here before was our omega. That's the angular velocity of the Earth. The angular velocity of the Earth, now that we've launched the space shuttles, has changed to be this. Meaning we sped up the speed of the Earth. What do you think, Trav?
That's the coolest thing I've ever seen.
I hope that y'all enjoyed that video as well as I did. As you can see, just by using simple physics and the law of conservation of angular momentum, we were able to speed up the Earth's rotation today quite significantly. So you probably won't notice the Earth sped up, but it did. You may have fell over at some point in the day, I don't know. But now you're going to live longer thanks to our experiment today. So anyways, have a good day. Remember that the law of conservation of angular momentum